Hello, this is going to be a brief video on what pointers are, how they work, and how we can use them in C to achieve similar sort of effects to the things we've seen in assembly. So first off, what is a pointer? A pointer is simply just a memory address. We've already seen memory addresses before in assembly, right? It's just a number that tells you where something lives in memory. So to give an example, suppose I declare in C an integer. So I'd say like x is an int, and it takes on the value of 6. What does that do in practice? It means somewhere in memory declares a box, and the box is labeled x, it contains a 6, and then x itself has to live somewhere in memory. Who knows where the compiler will decide to put it, but we'll say for the sake of example, it lives at memory address 100. So that's what an int is. I can then have something that points to that int, or something that tells me where that int lives in memory, and we call this a int pointer. So the type in C will be int star. This indicates that the following variable will be of type int pointer. That is, it's a memory address of where a integer lives. I'll call it p. And I'll allow p to take on the address of x. So we have this special symbol, the ampersand, which is called the address operator. So that means p takes on not x, so we don't put 6 into p, we put where x lives into p. In this case, the value of 100. So this basically declares another box. Its name is p. It lives who knows where. Let's say for the sake of example, it lives at memory address 110, and the value of p is 100. That is, p tells me where x lives, or p points to x. So that's what a pointer is. There's two main operators in C when it comes to dealing with pointers and memory addresses. There is the address operator, and the address operator basically takes a variable and tells you where it lives. So you can think of this as sort of broadly a variable to address. And we also have the sort of the opposite of this. We have the dereference operator, which is noted by star. And the dereference operator basically takes a pointer or a memory address, whatever you want to call it, and looks up what lives there. So this sort of does the opposite. This sort of takes an address and returns a value. So for example, if we were to just ask C what the value of p is, of course that's going to be 100. If I asked for star p, this would be not the thing, not the value of p, but the value of the thing that p points at. In this case, p points to x, and x is 6, so star p would be 6. We could also use the address operator on p, which would be not the value of p, but the location of where p lives, which would be 110. Because x is an int, and p points to x, that makes p an int pointer. Similarly, I could define a new variable, q, that tells me the address of p. So q tells me where p lives. That would make q a pointer to an int pointer, or a int pointer pointer. So we denote that with this following type. So this denotes that q is a pointer that points at int pointers. And so similar as the other two cases, I'll have a box. The name of this box is q. It will contain the value of where p lives, which was, I guess, 110. And then q itself lives somewhere else in memory, maybe 120. So what I'd like you to do now is I'm going to write up a handful of expressions in C, and I'd like you to try and work out what the value of these things are. So we've got x, ampersand x, p, ampersand p, star p, ampersand q, q, star q, double star q, and triple star q. So I've already given you the value of a couple of these things. I want you to pause the video for a moment and try to work out what the value of each of these things are. I'll assume you've done that. So let's go through the values of these things together. So x, the value of x is just whatever number lives inside the variable x, which of course is 6. So this is 6. Ampersand x is the location of where x lives. So this is going to be 100. P is just the value that lives in the variable p, p being an int pointer, which is 100. Ampersand p is where p lives, address 110. Star p is where p points, so the thing that lives at the memory address described by p, which is 6. Ampersand q is where q lives, 120. Q itself is just the value of where p lives, which is 110. Ampersand q is the thing that q points at, which is 100. Star q is a little more tricky. It's the thing that q points at and the thing that that value points at. So star q is 100, so this evaluates to star 100, which is the thing that 100 points at, which is 6. And the last one's sort of a bit undefined. Star q, I guess, would be the thing that lives in the 6th memory address in memory, which is, who knows, uninitialized garbage. But it's the thing that lives in memory address location number 6. Okay? So that's a brief intro to pointers and operations. Let's now look at an example where we can practically use pointers to do something. So in C, much like in assembly, an array is just a contiguous block of memory. When I say contiguous, I mean all of the elements are sort of right next to each other. So I'll write an example in assembly, and then I'll write a similar example in C so you can see the difference. So suppose we've got an array, and I want to store the numbers 6, 5, 9, 3. What would this look like in assembly? I guess I would have to define a label. So we have label array. This would be in the .data section. And then I just write .word, and I shove those numbers in. 6, 5, 9, 3. And of course, what does this do in practice? It means that somewhere in memory, I guess at the .data section, when it starts at memory address 0x200 whatever, this address I think, there'll be a 6. And then the next memory address, in fact I'm going to delete some zeros here just for the sake of my explanation. We'll pretend it's memory address 200. And then the next memory address, 4 bytes over, because an int takes up 4 bytes on the disco board. So address 0x204 would be a 5. And the next address 208 would be a 9. And the next address after that, which would be 0x209 ABC, would live a 3. So that's what this looks like under the hood, right? In C, it's very, very similar. So let's see what this would look like if I wrote it in C syntax. So to declare an array, I have to specify what the type of the array is. So I'm going to declare it as an int array. I'll give it a name. I could give it the name array, but I don't want to imply that array is a keyword, so I'll give it a silly name. I'll call it banana. These are square brackets to indicate it's an array, and then I can initialize my array by writing out the elements that live inside. So in this case, 6593. And this will do precisely the same thing that assembly does. It will, somewhere in memory, I don't know where, it's up to the compiler to decide, but somewhere in memory, it will place these numbers 6593 in consecutive order, and also it will declare a place to store banana, which is actually a int pointer. So somewhere, who knows where else in memory, we will have a variable called banana. It will live at memory address, let's say 0x300, and it will have the value inside of 0x200, which points to the start of the array. Now if we want to pull items out of my array, we can use array dereferencing syntax, which is sort of exactly the same as syntax that you already know from Python. So if I want to write banana of 0, this would fetch, that's a cool looking 0, banana of 0, there we go. This would fetch the first thing in the array, which of course is the 6. To no surprise, you could fetch any element in this fashion. So banana of 1 would be the second item in the array, which is 5, and sort of so on and so forth. What's actually going on under the hood here? Well, much like in assembly, all that's really going on is it's loading from the memory address with an offset. If I wanted to fetch the first thing from the array here in assembly, what would that look like? Well, I need to load the base address, that is the label, into a register first. So load R0 array. And then afterwards, I'm going to load from that location with an offset. So load, say into R1, R0 offset by 4. And that would fetch this number here, right? In C, it's something quite similar. When we do banana of 1 and we get 5, what's actually happening on under the hood is that we take the pointer, banana, which here represents the number OX200. We add 1 to it, and then we dereference the result. Now this isn't really adding 1, because if I were to add 1, I would be reading from address OX201, which would kind of read like 3 bytes from this number, these 3, and then a byte from the next number, and it sort of read out gobbledygook, right? Well, thankfully, C knows the type of this array. It knows it's an int array. And because it knows that, when I add 1 to a int pointer, the actual amount that it adds is 1 times however big an int is, which on the dev board is 4 bytes, but on different architectures, on different computers, this could be a different amount. On a 64-bit machine, an int is usually 8 bytes. So thankfully, we don't need to juggle how big the byte is like we have to do in assembly. C handles that for us quite nicely. And so this is good because then you don't have to manually offset by, multiplying by the size of whatever it is that you're storing. Now, this can get tricky if you don't know the thing that you're pointing at, and these are called void pointers. So in C, I could declare void pointer P to be equal to banana. What this would give me is it would give me a new box. The name of this variable is P. It lives, I don't know where it lives, let's say OX400, and it contains the number OX200, which points to the start of the array. A void pointer is special. It's a pointer that doesn't know the type of the thing it's pointing at. It's just a memory address. In assembly, all we have is void pointers. We don't have typed pointers, so we have to manually juggle ourselves how far to offset by and how big is the thing that we're loading. Is it a byte or a half word or a full word? I mean, I don't know, right? We have to manually juggle that ourselves. The assembly language isn't aware. Similarly in C, if you have a void pointer and you want to offset, you have to manually prescribe how large the offset is. So if I want to fetch the 5 instead of the 6, I have to go P plus 1 times however big an int is. How big is an int? I mean, I don't know. It depends on the hardware you're programming for. So in general, to make your code portable to run on any platform, you can write size of int and then dereference the result. So this would go, take the pointer P plus 1 times however big an int is on your platform. On the dev board, it's 4 bytes. On different platforms, who knows? And then dereference the result, which would successfully pull out the 5 from the array. And in fact, that's actually precisely what this syntax does. When I write banana, fetch me the nth thing from the array, this is literally just a nice sugary syntax for banana plus n, dereference the result. These are quite literally the same thing under the hood. So now we've seen what pointers can do for one-dimensional arrays. I'm going to move on to an example with two-dimensional arrays and how to operate with that. So we can get rid of this. And now I'm going to talk about strings, which in C is just an array of characters with a null terminator on the end. So suppose you want to do a string in C that is a sequence of ASCII characters. I can write char, and then I'll call my string hello. It's going to be an array of characters, and then I can just initialize it by writing the string, in this case I write the string hello. Okay, so what does this look like under the hood? I've got an array of bytes somewhere in memory, who knows where. Let's say it starts at memory address 100. I'll have the character H, which in reality will be stored as the ASCII value of the character H, which is whatever it happens to be. And then we'll have the ASCII character E, ASCII character L, L, O, an exclamation mark. And then finally, the last hidden character is a null terminator. So this string, despite being 6 characters long, actually takes up 7 bytes in memory, because a string is always terminated with a special null terminator. The reason why we do this is so when we read the string out of memory, I know where the end of the string is, right? So perhaps we could demonstrate this by writing a function to compute the length of a string. So what's my function going to take as input? It's going to take a char pointer. So in fact, I haven't defined the char pointer here, so I had my array. I'm going to have another box called, that's the variable hello, that contains the memory address 100, that points to the start of the string, and this lives at, say, memory address 200. And of course, because characters are 1 byte, these would all be in consecutive memory addresses. There we go. So maybe pause the video for a moment, see if you can try to write a function in C that will compute the length of a string. So the type of that function, it's going to return an int. I'll call the function length, and it takes a char pointer to a string. Okay, so have a go at that. I'll assume you've done so. So let's see how we can do this together. So what I'm going to do is I'm going to load the thing from memory that the pointer points at. And if it's not a null character, then I'll move to the next character, sort of keep track of how many characters I had to look at before I got to the null terminator. So I'll define a variable to keep track of the size, so int size equals 0. And then what I'll do is I'll look up the thing that lives there, and if it's not a null terminator, I'll add one to the pointer, and then I'll keep looking. So I'll write a sneaky while loop. I'm going to go while the thing that stir points at is not null. So while dereference stir is not equal to 0, I'm going to add 1 to the size. So size plus equals 1. And then I'm also going to add 1 to stir itself, to move it to the next character. Okay? And then when my while loop is done, I can just return size. Okay? So let's check that this function works by running it on this example string here. So I suppose I've got a pointer, I'll call length on hello. Hello is a char pointer, so that all matches up. And so let's run the function. So we have size is initialized to 0, and my pointer stir is the same value as hello, which will be the number 100. Okay, so while dereference stir is not 0, so if I dereference stir, what lives at memory address 100? The ASCII character H, which is some non-zero number. So we enter the while loop, plus 1 to the size, plus 1 to stir. And then run it again. Is stir pointing at a null terminator? No, it's not. It's pointing at E. So increase the size, increase the stir. And we sort of rinse repeat this until I get up to the point where I've counted 6 characters. 1, 2, 3, 4, 5, 6. So the size will be 6, and stir will be 1 of 6. And then what happens next? So fetch the thing that lives there at 106. It's a null terminator, so we exit the while loop, and then I return the size of 6. So that's the function that computes the length of a string. Okay? So now we've seen what a string is. Now we can deal with something nastier, an array of strings. So get rid of this. So what does an array of strings look like? Well, we know what a string is. It's just a char pointer to a contiguous block of memory full of chars with a null terminator. So an array of strings will be a char pointer pointer that points to an array of char pointers. So let's see what it looks like in practice. So I might define char star, I'll call it dict for dictionary. It's going to be a dictionary full of words. The glare on that's pretty bad, so I'm going to move that down a bit. That's better. Okay, it's an array, and what's inside? A bunch of strings. So I'll just pick some easy short strings, maybe cat, dog, and home. Okay, those are my strings. What does this look like in practice? It's really up to the compiler where it decides to store these strings. It will store them anywhere in memory, but more likely than not, it's probably going to put them all consecutively next to each other. So let's assume for the moment that it does do that. So we'll pretend it starts memory address 100, and then we have 101, 102, 3, 4, 5, and so on. We'll keep adding memory as we need it. So cat, and then a null terminator. This is the first string. And then we'll have dog, so D, O, G, and then the second null terminator. Got enough room here? Yeah, we'll have enough room. And then home, so H, O, M, E, null terminator. 8, 9, 10, 11, 12. Does that all fit in the screen? Just barely. Wonderful. So C will put all these strings in memory, probably consecutively. And then it will also declare an array of char pointers. How big is a char pointer? It depends on the platform that you're on. The Disco board is a 32-bit machine, so its pointers will be 32 bits or 4 bytes large. Where do they live? Who knows? Let's make up some numbers. So 200, 204, 208, that's where they live. First pointer will point to the start of the first string, which is memory address 100, so that points here. The second pointer will point to the start of the second string, which is 104. And the third pointer will point to the start of the third string, which is memory address 108. And the last thing is that dict is a char pointer pointer that points to this array of char pointers. And it lives at, let's pretend memory address 300, and then has the value 200, so it points here. So that's what this thing looks like, sort of under the hood in memory. So if we want to fetch something from memory without using array dereferencing syntax, we can do that using pointer arithmetic. Suppose I wanted to fetch the G, the third letter in the second string. Well, we could do that with array dereferencing syntax. That would simply be dict, and then fetch the first string, again, remembering we index from 0. And then of that array, again, arrays are just pointers to blocks of memory, fetch the 0, 1, 2 second character. So this would return G, and then what's actually going on under the hood, we take dict, we add 1 to it, 1 times however big a char pointer is, but because dict is a char pointer pointer, C knows how big a char pointer is, so this will really be 1 plus however much I need to offset by to get to the next char pointer. I dereference this, and then I add 2 to the result, and then I dereference that. So this is exactly the same as this, and that will fetch me the G from memory. Now, a lot of people say that C is sort of like an unsafe language, and this is a really good example of why. Suppose, like, I don't know, this was my password is cat, and this was your password, and your password is dog. Presumably, you'll have a pointer, maybe it's your password, and it points to the start of where your password lives in memory. Let's say, so this is memory address 104. The problem is you could access things you're not really supposed to be allowed to. So if you took your pass and then your pass indexed at 0, that would of course fetch the first letter D, your pass of 1 would be the O, and your pass of 2 would be the G. Problem is, C is a very literal language and will not check error bounds or check anything silly. So if you were to write your pass of 5, C will do exactly what you asked it to do. It will go to here and offset by 5 times however big a char is of 5 bytes. So 1, 2, 3, 4, 5, it would fetch the O from the next string over. So maybe stop and think for a moment. How would you read out my password here in memory, which is cat, using only a pointer to your string dog? So how would you do that? Well, the start of my string is 1, 2, 3, 4 places back in memory. So if you were to just go the -4th element in your string, which in most other languages would be an error because you're out of bounds, C will very happily fetch that thing. It will literally go to here, 1, 2, 3, 4, and it will fetch the C. -3 would fetch the A, and -2 would fetch the T, -1 would fetch the null terminator, so you know you're out of string, and ta-da! You managed to steal my password out of memory. So that's what people say when C is a sort of an unsafe language. It doesn't check boundaries, it barely checks anything. Especially if you're writing code on the dev board where there's no operating system and no one to stop you. If you want to read and write to some arbitrary memory address, I mean, go for it. No one's going to stop you, right? So that's why sometimes C is referred to an unsafe language. So now I've talked about that. The other thing I want to talk about is structs, what they look like, how to use them, and how they tie in with pointers. Okay, so what's a struct? A struct is basically a way to cobble together multiple bits of data in memory somehow. So a struct looks like this. I'll call my struct food because I'm particularly unoriginal. And I'll say that my struct has 2 elements, maybe an integer called x and a char called y. Okay, I'm not entirely sure about whether the food goes here or here. I always forget. You should look that up. And so what can we do with this? Well, basically, when you declare a struct, which we can do as follows. Struct foo, so this whole thing is going to be the type. And I'll give my struct a name. I'll call it maybe my foo. No, it's a bad name. I don't want you to think it's a keyword. I'll call it apple, something absurd. What this basically does is it declares 2 blocks of memory. So we have a block of memory to store the integer x, and we have a block of memory to store the char y, and then apple will be the location of this thing in, careful David, sorry, this will be apple. Yeah. And so apple will be a variable that takes up 2 slots in memory, 1 for the x and 1 for the y. So if I want to store things in my struct, I can do that by writing apple.x, and then I can store a 6 in the x, and I can write apple.y, and then store, I don't know, a character in the y. And then C will magically, automatically work out what offsets to store things what. So it'll put the 6 here, and it'll put the A there. So that's how we can sort of implement like a tuple in C by using a struct. What's this useful for? Well, suppose you wanted to store a collection of data for, I don't know, maybe like a character in a video game, and you had like their health and their mana and their abilities and all this sort of stuff. You can imagine packing that information together in like a character struct that would store all that parameters. You could then, for all the characters in your game, you could have like an array of character structs. And remember the example from the Morse code lab? We had to manually offset by like 24 bytes each time because that was the size of a row in the Morse code table. In C, you won't need to do that. If you've got a pointer to like a Morse code table, and it knows the definition of one row in that table defined as a struct, you can just use the normal standard array dereferencing syntax and fetch the element that you want. Suppose we had another struct, struct foo, I don't know, banana. I could then store these things in an array of structs. So I could have struct foo, call my array stuff, square brackets, and it contains inside two structs, banana and apple. In its usual fashion, C will just put these two things into memory right next to each other. So I'll have one struct. First struct will be banana, which will store some integer and some character. And the second struct will be apple, that stores the next struct. And then of course stuff will be a pointer that points to the first element of this array of structs. So that's how we can store like a tuple or multiple objects in an array concurrently. So this could be useful for like a database or something like that. The other thing I want to talk about next is linked lists. So we saw this example in the lab, but I think it's important enough to worth mention. What a linked list is a linked list is a different way of storing data as compared to an array. An array is a contiguous block of memory, which is all well and good if you're just looking up items in the array, because we just have to offset to jump to the place where you want to go. But if you want to insert an element into an array, that can be quite expensive. You have to basically pick up the rest of the array and sort of shuffle it down in memory. Linked lists excel in this regard in that they're very easy to edit. So I'll first describe sort of intuitively what a linked list looks like, and then we'll go through how we can define such a thing in C. So what a linked list looks like is each element in the linked list contains two bits of information. The first bit of information is the element stored at that location, so maybe this one stores a 3. And the second piece of information is where the next element in the linked list lives. So maybe this lives at memory address 100, and then the next thing, which will be a linked list pointer, lives at 104. This will contain some number 200, which tells me where the next part of the linked list lives. This could contain a 6, and maybe the next part lives at, I don't know, address 150. They don't have to be in consecutive order, they can sort of be all over the place. That's kind of the whole point of a linked list. So this would be over here. This could be a 9, living at memory address 150, and then 154 could contain a 0, which is called like a null pointer, which sort of represents that's the end of my array. So the list of numbers 369 stored as a linked list would sort of look like this in fashion. So each element and then is adjacent to a pointer to where the next element lives. So how do we do this in practice? Well, we could use a struct. So I could define a struct. I'll call it our LL for linked list. It's going to contain two things. It's going to contain a node of type int, that's sort of the value stored at the location, and it's going to contain a pointer to another linked list. So it's going to contain a struct linked list pointer, I'll call it next. Okay? So if I wanted to define this particular array, again I've sort of made up the memory addresses because it's beyond me where C will decide to store them, but we can define it anyway. I'm going to define it backwards because to define each element I need to know where the next one lives, so I'll do this in backwards order. Struct linked list third is going to equal, so it's going to store two things. First thing is going to be this number here, the 9, and the second thing is a pointer to the next element. Now this is the last element in the array, so there's nothing for me to point at, so I'm just going to put a dummy value here of 0. And 0 is a special memory address in C, in that you can never load anything from the 0th address in C. If you try to load something from the 0th address, you'll get some error message about dereferencing a null pointer and your code will crash. This is quite deliberate. So that's the last element. The second to last element, struct LL second, will contain the number 6, and it will also contain a pointer to the next elements. It will contain the address of where third lives, which I can write as ampersand third. And then we have the first element in the linked list, which points to the second. So struct linked list first, which contains the number 3 and points to the second. Okay, and there we go. So that's the way we can, one way we can initialize our linked list in C. So what might be a good exercise is to see if you can try to work out how to write a function that extracts out the last element given a pointer to the start of linked list. So suppose the only piece of information that you've got is some pointer that tells me where the first thing in the linked list is. We have to try and extract out the last element. Okay? So maybe sort of have a go at that, see how far you can get, and then I'll show you the solution. Okay, so I'll assume you've done that. Let's see what the solution is going to look like. So it's going to return int, and I guess we'll call it maybe last. And it takes a pointer to a linked list structure. So it takes a struct LL pointer. I'll call it PTR for pointer. And so how are we going to do this? So I have to check if this pointer is pointing at a struct where the second element is a null pointer. Because if it is, that means I've found the end, right? So and I want to basically have a loop to check that. And every time it isn't a null pointer, I move to the next element. So I can have while, you must be careful here, dereference the pointer will fetch me the struct. And then I want to fetch the next part of that struct. And I want to keep doing this while it's non-zero. Make some more room there. If this particular syntax strikes you as ugly, I'm inclined to agree. In fact, there's a nice way to dereference a pointer and then take something out of the struct that lives there. And you can do this using the arrow operator. So we can instead write pointer, and it's just like a hyphen and then a greater than symbol. So what this means is while the pointer is pointing at a struct where the next element of that struct is not 0, do stuff. So what am I going to do? I'm going to replace the pointer with whatever this pointer is. So that will look like pointer equals pointer arrow next. And so I'm going to repeat this loop until I've got a null pointer, and then I'll just return the node that lives here. Return pointer node. Okay? I believe that works, but we should probably run it and find out. So let's suppose we've got this example here. Pointer is got the value 100, it's pointing it here. So while pointer is pointing at a struct and the next thing at struct is not 0, so dereference, we get the struct. The next element is the second part, which is not 0, so we run the loop. Pointer is replaced with pointer arrow next. So we take this value and copy it into the pointer, which is 200. So now it points to the second part of the struct. And then repeat again. Dereference, is the second part 0? No. So we copy this part into the pointer, which would be 150. And that means the pointer would now point at the third element, which is here. And repeat once more. Is the second thing this is pointing at a 0? Yes, it is. So we terminate. We return pointer, dereference, and fetch the node element, which would return a 9. Okay? So that's what linked lists look like under the hood. If you'd like some more material, this is all covered in, I believe, Lab 9, so you can go back and have a look at that again. There's also a lengthy post on Piazza that I made, sort of about pointers, so I'd direct your questions to there as well.